We can see here the interpolation-based approach has some very large biases, and the values are off by quite a bit. And so to summarize on the MACA method, the resolution currently is daily, 8 kilometers. The end products are high temperature, low temperature, high relative humidity, low relative humidity, 10-meter zonal and meridional wind, and then finally the accumulative precipitation. Theoretically, this downscaling method is driven by daily synoptic weather from GCMs, so there's no need to temporally disaggregate, as which is done by other methods. So the current data availability from the CMIP3 models, there's 13 different models. These models were chosen on the basis of actually having high, low temperature, near surface specific humidity, surface wind speeds, and precipitation. And the time slices are 1971 to 2000, and then these two future time periods from the A1B scenario. You can actually acquire some of the downscale data sets for the Western United States, both the monthly BCSD method produced by Von Walden and Brandon Moore. That's available at 4-kilometer resolution from over 20 GCMs. And then also you can actually acquire daily data from the MACA method, as I described here, from inside Idaho. Finally, as we move on to some of the more dynamical downscaling methods, we move into the realm of regional climate models. And these are basically mesoscale models that are currently used in numerical weather prediction. And they're advantageous in that they're able to resolve sub-grid scale processes, physically resolve processes that are otherwise parameterized by the GCMs themselves. And what it is important though to note that at large scales the regional models are forced by GCMs themselves. So the GCMs are basically providing initial conditions, so sea surface temperature, sea ice, soil moisture. These are updated through an iterative process as we move down into regional climate domains. There are a couple experiments that are actually going on now that I'd like to mention. One is the NARCAP experiment. It's a multi-model, multi-regional, multi-global model and multi-regional model ensemble where they're basically pairing global models with regional models. The output is at 50 kilometers and 3 hourly, and so that's a database that is being populated currently. And then there's also a regional climate experiment being done by climateprediction.net, and this is basically a perturbed physics runs that's gauging climate sensitivity, and the domain of interest here is the Western United States, and the data is 25 kilometer, 3 hourly. And so regional climate models are clearly the next step. However, there are some problems in terms of direct application, since that's what we're interested in after all. The problem here is that these regional models do not account for some of the biases in the GCMs themselves. They can actually act as a bias multiplier, and the output of the regional models are inherently biased. So there's some problems with direct application. So that's another problem. There's also a relative lack of multi-member ensembles, and these regional models are fairly expensive to run. So in terms of a probabilistic view of climate projections, we're currently not quite there when it comes to regional climate models. However, there are some future steps, and I think that a marriage between dynamical and statistical downscaling will be quite fruitful. We can basically envision using regional climate scenarios such as the ones I mentioned at 25 or 50 kilometer resolution, and then applying some of the downscaling methods that I went through. So the daily BCSD, that would be a perfect one to basically take your regional data at 25 kilometers, adjust for the biases, and then actually adjust for some of the subgrid scale issues. Most downscale data sets that are currently available are not tailored for individual needs. And a great example of that is the needs of meteorological and climatological data to assess fire danger. So we can think about a few of these needs. In terms of fuel availability and flammability, lower frequency climate information is an important driver. However, as moved into summer, we realized that higher frequency climate data, meteorology, becomes more and more important, particularly when we're thinking about fuel moistures, fire behavior in different vegetation types. And so the need here was to move to daily timescales to incorporate additional variables besides monthly temperature and precipitation. And from the perspective of fire danger, that requires the integration of winds, relative humidity, and insolation. We also know that extreme fire danger is pronounced in regions of complex terrain, and it turns out that regions of complex terrain necessitate downscaling to begin with. And then finally, it's important to actually integrate these metrics of downscale data into terms that are actually usable by stakeholders. So in this case, in terms of fire management, fields like temperature, humidity, precipitation may be useful on their own, but it may be more informative to actually integrate these into metrics that are currently used and known. And so we can think about this as really moving beyond just temperature and precipitation. And the interest here is to really highlight areas of risk. And this gets us to start to think about the spectrum of climate and meteorology as it really relates to fire itself. And so we think about antecedent conditions involving snow water equivalent, mountain snowpack, changes in moisture, availability and timing, and then finally things like the frequency of extremes. In this case, we can think about extreme fire danger. And so one of the metrics that's used frequently is the energy release component, which is basically a hybrid climate weather index, which is a good proxy for fuel moisture, and also relates very strongly to the likelihood of a large fire. And so we're looking here at a multi-model perspective of changes in ERC between the mid-21st century and the observational period of the late 20th century. And we're breaking this down into 4 different time periods trying to encompass fire season. So fire season generally propagates from the southern deserts beginning in the springtime up into the Great Basin and northern Rockies into summer. And we know from climate models themselves that there is generally a poleward retraction of the jet stream, which initially affects the southwestern United States during the spring and fall, or during the springtime, which is the beginning of their fire season. And then finally here, as we move into summer, a lot of the models are suggesting a significant decrease in precipitation across the northwestern tier of the United States, which is basically a response to the northward shift in the jet stream and a lack of storm systems moving through and dropping the occasional amount of precipitation to increase fuel moistures. Along with changes in the dynamic storm track, increases in temperature can also lead to increased evapotranspiration, which can then lead to increased moisture deficit. So when we couple those two things together, we basically get an earlier onset of the dry season, or in the perspective of fire management, the fire season. And so we see these significant increases in fire danger across the Southwest in spring and early summer, and then during the core of summer across the northwestern portion of the United States, the northern Rockies and the Cascades, we see a significant increase in fire danger. And we can then translate that into extremes. So we can think about how that might change the frequency of extreme or high fire danger days. And these high fire danger days are currently used as kind of indicators for certain management actions. And what we can basically start to point out here in a multi-model perspective are areas where we see an agreement amongst the models. And so where do we take this? How do we go forward with this? And I think this is really an iterative process whereby we actually, as scientists, get information from end users or how some of the data may be applied, and then go back and figure out how we might want to rework our downscaling methods or the way that we select our GCMs. And I think it's important here to point out that a one-size-fit-all approach for downscaling or assessing climate change risk is probably not likely, and that we may need to look at specific types of downscaling for certain types of impacts. So low risk, high impact events, these may be extreme flooding events. They may be looking at wind events, for example. So I think the idea here is that if we can continue a dialogue between climate science and then the users of some of the data sets, ultimately we'll hope to increase the value of these end products in science delivery.